Welcome to Introduction to Sedimentation and Stratigraphy. Today we'll be talking about deltas. This is part 1 of 3, where we focus on types of deltas. A delta is a body of sediment that builds outward from the mouth of a river into a sea or a lake. They are found along many modern shorelines where they form flat terrains suitable for agriculture. The morphology of a delta is determined by a combination of upstream controls, principally discharge and sediment supply, the water depth that it builds into, and processes along the shoreline such as waves, longshore drift, and in some cases, in marine settings, tidal processes will be important. This results in a mosaic of depositional sub-environments in deltaic settings, each with their own variable characteristics. Deltas in the stratigraphic record display a range of facies characteristics that record the combinations of processes of their formation. The relative importance of river, wave, and tide processes can be recognized in delta deposits, along with information about the sediment, including grain size distributions and water depth from sediment body thicknesses. A delta can be defined as a discrete shoreline protuberance formed at a point where a river enters the ocean or another body of water, and as such, it's formed where sediment brought down by the river builds out or progrades into the body of a lake or sea. In contrast, an estuary is a river mouth where there's a mixture of fresh and seawater with an accumulation of sediment within the confines of the estuary, but without any buildup outward into the sea. Deltas are widely variable in terms of scale, processes, and the nature of sediment deposited. A stream feeding into a lake, for instance, may create a sediment body that's only a few tens to hundreds of meters across, whereas the biggest deltas may cover thousands of square kilometers. Mouths of rivers are where accumulating detritus forms a sediment body that progrades or builds out into a sea or lake. In marine environments, interaction of subaerial processes with wave and tide action results in complex sedimentary environments that vary according to the relative importance of a range of factors. Delta form and facies are influenced by size and discharge of rivers, energy associated with waves, tidal currents and longshore drift, as well as grain size and water depth. They're almost exclusively sites of clastic deposition, ranging from fine muds to coarse gravels. Deposits formed in deltaic environments are economically important in the stratigraphic record as sites for the formation and accumulation of fossil fuels. The mouth of a river is the point where it reaches a standing body of water, which may be fresh, brackish, marine, or hypersaline. These are places where a delta may form, an estuary may occur, or where there is neither a delta or an estuary. This variation depends on the morphology of the river mouth, the supply of sediment by the river, and processes acting in the lake or sea. A delta forms when sediment is carried by a river and progrades into another body of water. In contrast, an estuary is a river mouth with a mixture of fresh and seawater, an accumulation of sediment within the confines of the estuary without any buildup into the sea. Ordinary river mouths are settings where there's no significant mixing of waters, and any sediment introduced by the river is reworked and carried away by processes such as waves and tides. Modern deltas vary widely in terms of size, processes, and nature of sediment. A stream feeding into a lake may create a sediment body that is only a few tens to hundreds of meters across, while the largest deltas cover areas of thousands of square kilometers. The original delta is the mouth of the River Nile in Egypt, an area with river channels that had the triangular shape of the fourth letter of the Greek alphabet, delta. This is a relatively rare delta shape, however. Many other deltas have morphologies that range from elongate fingers building out into the sea, such as the Mississippi Delta in the United States, to highly indented shapes formed by multiple channels, such as in the Ganges Delta of Bangladesh. The overall form is found to be related to the relative importance of 3 main processes: the current in the river, the action of waves, and the action of tides. Sediment deposited in the Mississippi and Ganges deltas is primarily mud and silt, but others, such as the Rhone Delta of France, are much sandier, while deltas fed by pebbly streams can contain significant amounts of gravel. Gravelly deltas are not necessarily fed by a river, however. A debris flow or sheet flood dominated alluvial fan may build out into a lake or sea to form a sediment body that is commonly referred to as a fan delta, although it should be noted that the term fan delta is also applied to coarse-grained deltas fed by rivers, just to add some confusion. Deltas are generally classified by dominant grain size of the deposits and the relative importance of fluvial wave and tide processes. To characterize that, we use what's called the Toblerone plot. Sediment supply is determined by climate, influencing the weathering and erosion processes and discharge, while tectonic controls on the topography, particularly the gradient of the river, that determines the grain size of the material carried. The relative importance of processes that rework the sediment in the basin is controlled by climatic and geomorphological factors, with tidal range determined by the local shape of the basin, while wave activity is influenced by climate and the size of the water body. Water depth is another variable used to classify deltas. Water depth in the basin is important because it influences the effects of wave and tidal processes as well as the geometry of the delta body. If a delta is building out into shallow water, it will spread further out into the basin than if the water is deeper. Marine deltas form at the interface of continental and marine environments, with processes associated with river channel and overbank settings occurring alongside wave and tidal action and their effects. Flora and fauna characteristic of land environments, such as the growth of plants and the development of soils, are found adjacent to exclusively marine animals. Deltas can therefore be compared in terms of sub-environments, divisions of the overall delta environment in which these combinations of processes occur. Deltas are fed by a river or alluvial fan, with a transition between the area that is considered part of the fluvial-alluvial environment and that considered to be the delta top or delta plain. Delta channels can be as variable in form as a river and may be meandering or braided, single or divided channels. Branching of the river channel into multiple courses is common to create a distributary pattern of channels across the delta top. Coarsest delta top facies tend to be found in channels where flow is strong enough to transport and deposit bedload material. Adjacent to the channels are subaerial overbank areas that are sites of sedimentation of suspended load during channel flooding. These may be vegetated under appropriate climatic conditions, and in wet tropical regions, large vegetated swamps may form on the delta top. These may be sites for the accumulation of peat, although if there's frequent overbank flow from the channel, the deposit will be a mixture of organic and clastic material, ultimately forming a carbonaceous mud. Crevasse splays may result in lens-shaped sandy deposits on the delta top. On deltas where the channels build out elongate lobes of sediment, sheltered areas of shallow water may be protected from strong waves and currents. These sheltered areas along the edge of the delta top are called interdistributary bays, and they are regions of low energy sedimentation between the lobes. The water may be brackish if there's sufficient influx of fresh water from the channel and overbank areas, and the boundary between the floodplain and the interdistributary bays may be indistinct, especially if the delta top is swampy. Flow velocity at the mouth of the channel is abruptly reduced as the water enters the standing water of the lake or sea. The delta front immediately forward of the channel mouth is the site of deposition of bedload material, usually as a subaqueous mouth bar. The coarsest sediment is deposited first, in shallow water close to the river mouth where it may be extensively reworked by wave and tidal action. The current from the river is dissipated away from the channel mouth, and wave energy decreases with depth. This leads to a pattern of progressively finer material being deposited further away from the river mouth. This area, known as the delta slope, is often shown as a steep incline away from the delta top, but the slope varies from only 1 or 2 degrees in many fine-grained deltas to as much as 30 degrees in some coarse-grained deltas. Riverborne suspended load enters the relatively still water of the lake or sea to form a sediment plume in front of the delta. Fresh river water with suspended load may have a lower density than saline seawater, and the plume of suspended fine material will be buoyant, spreading out away from the river mouth. As mixing occurs, deposition out of suspension occurs as well, with the finest, more buoyant particles traveling furthest away from the delta front before being deposited in the pro-delta region. Gravity currents may also bring coarser sediment down the delta front and deposit materials as turbidites. When clay-loaded water reaches the ocean, the change in ionic strength induces a change in the behavior of the clay particles. They flocculate and drop from suspension. The definition of a delta includes the concept of progradation, that is, deposition results in the sediment body building out into the lake or sea. The sedimentary succession formed will therefore consist of a progressively shallower facies as the pro-delta is overlain by the delta front. which is in turn superimposed by mouthbar and delta top sediments. The succession formed by the progradation of a delta, therefore, has a shallowing up pattern, a series of strata that consistently show evidence of younger beds being deposited in shallower water than the older beds they overlie. In the delta front subenvironment, the deepest water facies, the pro-delta deposits, are the finest grained as they are deposited in the lowest energy setting. In a shallowing upward sequence, the fine-grained sediment will be overlain by sediment of the delta slope. That tends to be somewhat coarser. The shallowest facies will be those of the mouthbars that are usually sandy or even gravel-sized. Beds formed by delta progradation will therefore exhibit a coarsening up pattern. The shallowing up, coarsening up pattern is one of the distinctive characteristics of a deltaic succession, but it can be considered to be more diagnostic of a delta only if the top of the succession shows a transition from deposition in a subaqueous to a subaerial environment. Evidence of deposition on the delta top may be the recognition of a river channel, signs of plant growth and soil formation, or other exclusively subaerial physical, chemical, or biological processes such as desiccation cracks or tracks of land animals. Combinations of factors that control delta morphologies generate a wide range of delta characteristics. Modern deltas provide examples of a number of positions within the Toblerone plot. The Mississippi Delta is fine-grained and river-dominated. The Rhone Delta, on the other hand, is mixed sand and mud and is wave-dominated. The Skadara-Sander is mainly gravelly with river and wave influence, and so on. Even with all the possible positions within the plot, there are also additional variables of water depth to be added. Because classification of deltas into a small number of types will represent only a small proportion of possibilities, perhaps it's more useful to consider the effects of different factors on the delta morphology and consequently on delta facies, the form of the sediment that's deposited. The deposits on a delta will include a high proportion of fine-grained material if the fluvial system supplying it is a mixed-load river. Low-gradient, mixed-load river channels characterize the lower tracts of large river systems. Large rivers like these carry sediment that is delivered to the delta as sandy bedload and a large suspended load of silt and clay. Sand deposition on the delta top is concentrated in the delta channels and on adjacent levees, while the bulk of the delta plain and any distributary bay areas are regions of mud accumulation. Differences in the grain size of the sediment supplied affect the form of a delta. A high proportion of suspended load results in a relatively small mouthbar deposited from bedload and extensive delta front and pro-delta deposits. A higher proportion of bedload results in a delta with a higher proportion of mouthbar gravels and sands. Proximal mouthbars may also be sandy, but the rest of the delta slope and pro-delta receive sediment fallout from the plume of suspended sediment that issues from the river mouth. The delta front may also be the site of mass flows. Wet, muddy sediment brought down by the river may be transported by turbidity currents to deposit as turbidites on the lower part of the delta front in the pro-delta area and beyond. Deltas can be the supply systems for large submarine fan complexes. Muddy sediment deposited on the delta slope is initially unstable, and syndepositional deformation features are common. The proportion of sand in the delta deposits increases if the feeder river provides more bedload sediment. Sandy bedload rivers also transport material in suspension, but the delta environment becomes a setting for deposition of sand in channels as overbank splays on the delta top and as shallow marine deposits in the upper part of the delta front. Extensive sand bodies form as mouthbars, perhaps reworked by wave and tide action. Fine-grained deposition occurs in parts of the delta plain away from the channels and in the lower parts of the delta slope and pro-delta region. Coarse-grained deltas, also referred to as fan deltas, are fed by pebbly braided rivers or alluvial fans. They form adjacent to areas of steep relief where streams in the catchment areas of the rivers flow down steep slopes carrying coarse material into rivers or onto alluvial fans that prograde into a lake or the sea. Settings such as faulted margins of rift basins are typical sites for coarse-grained deltas to form. The delta top environment, and hence the facies deposited, are those of a coarse-braided river or alluvial fan. Gravelly material is transported by fluvial or alluvial fan processes into the lake or sea, where they're reworked by waves or tidal currents. Modern examples are documented from all basins where the tidal range is small and wave action is the main mechanism for distribution of clasts in shallower water. The energy associated with waves is strongly depth dependent, and therefore there's a sorting of sediment into different grain sizes according to water depth. The largest clasts remain in the shallowest water where the wave action is strongest, while smaller clasts are carried by waves further offshore into slightly deeper water. Across a gently sloping shelf, there'll be a progressive fining of the clast size as the water depth increases, and therefore the energy of the wave decreases. Progradation of a coarse-grained delta across a shallow lake or seafloor results in a coarsening up succession from finer sands deposited furthest offshore through coarser sands, granules, pebbles, and even cobbles or boulders at the top of the delta front succession. This is in turn overlain by coarse fluvial or alluvial fan facies of the delta top. Coarse-grained deltas that display these characteristics have been classified as shelf-type fan deltas. A delta prograding into shallow water will spread out as the sediment is redistributed by shallow water processes to form extensive mouthbar and delta front facies. In deeper water, the mouthbar is restricted to an area close to the river mouth, and much of the sediment is deposited by mass flow processes. Here we have a modern coarse-grained delta at the margin of Rift Basin. You can see the rapid drop-off in sediment as the gradient of the river drops from a few degrees to zero.